Assistant Professor in Chemical Engineering Department at LJ Institute of Engineering and Technology. The subject that I am going to take is Nanoscience and Technology. Right, so moving forward in this lecture, okay, we will be studying about your high energy ball milling. Okay, the concept is based on what? Mechanical attrition. So first of all, what is high energy ball milling? So you can see that it is a kind of grinder which is used to grind and blend the materials. Right? See, in mechanical operations you have already studied about crushers, gyratory crusher, okay? Energy means. So the concept here of high energy ball milling is just like that. So first of all, what we need to know that this type of method, okay, it comes under your top-down approach. It means from the bulk quantity, your size is reduced to the nanoparticle size. Clear? Now, what is the principle of its operation? It works on the principle of impact and attrition. Of course, in your ball mill, metal balls are used for the impact purpose. So when your mill, when it rotates, the ball, okay, because of the influence of gravity, they fall down onto your material, and because of that, that is your impact, the size reduction occurs. Now, how attrition takes place? Okay, see, as the mill rotates on its axis, right? So the material, it scrapes along the surface of your mill, and that is the effect of attrition. So because of impact and attrition, size reduction occurs. Okay, now how is it mechanism? So see, first of all, there is a hollow cylindrical shell which rotates about its axis. Okay, so as the cylinder, it rotates about its axis, the metal balls or ceramic balls, whatever the kind of material balls you're using, they also rotate with the horizontal cylinder, right? Now, it is partially filled with balls. So your balls, the material of construction can be what? It can be steel, it can be stainless steel, ceramic or rubber. Okay. So moving forward, here you can see that the length of the cylindrical mill, it is generally greater than its diameter. Okay. Now, how you can carry out the grinding? It can be either wet or dry. Okay. Then for effective production of amorphous material, generally for amorphous material you use high energy ball milling. So the properties of ball, whatever you're selecting, it depends on the size, density, hardness and its composition. Clear? What is the advantage here? That it is suitable for both open and closed grinding, and for batch and continuous operation, okay, and for all material of degree of hardness. Okay, so varied degree of hardness material you can use your high energy ball milling. Okay, so here you can see that this is the schematic figure of your ball mill, right? So in the figure A, you can see that here you have a cylinder in which your metal balls, let's say it's a metal balls, are kept. So here you can see that you have three components which are used for the size reduction. Okay, on three materials for which size reduction has been done. So you can see one is your braking phase and third is your welding phase. So you can see that how the three components are break down because of the shear fracture. Okay, because of the stress the material is break down. Now in the welding phase you can see that cold welding. So see, temperature is also important here. So you can see that when cold temperature is there, and now because of friction, a little bit of temperature increases. So you can see that aggregation of these three components is taking place. Okay. So you can see in the picture number C, all the three components, they are getting together in the form of aggregate. So now let's talk about how this aggregate affects. Okay. So see, you can see here in the figure B, your material, it can be the cationic, it can be anionic, or it can be neutral. Now as mechanical grinding occurs, if surfactants are not added, note down here the topic is about addition of surfactant. Okay, so if surfactant are not added, you can see that particle aggregation occurs due to high surface energy generated on the milled particles. Okay, here I am talking about if surfactants is not added into your grinding. So aggregation of particles occur. Okay, so that is not our requirement. We require that the bulk material is broken down into nanoparticle size. But if you're not adding the surfactant, these particles are aggregating into one another. Okay. Now, if surfactant are added, so you can see here, for your cationic material, you are using anionic surfactant. Okay, whereas for your anionic material, you are using your cationic surfactant, right? So, whereas for neutral, when your material is neutral, then you are using non-ionic surfactant. So, addition of surfactant, it prevents the material to aggregate. Clear? Now, what are the factors to be considered when you are choosing the ball milling? Okay, so it depends on the types of mill. Okay, once again, the mill, the cylindrical vessel. Okay, whatever the mill vessel is, it depends on that mill. The temperature conditions. Third is your milling speed. Already in mechanical operation, you have studied about the critical speed of operation. Okay, then the milling time. Fifth is your ball to the powder weight ratio. Sixth is the milling atmosphere. Atmosphere, it means it can be inert, acidic, basic, whatever the atmosphere we are talking about. Now let's see the types of mill. So here you have 6 figures, okay, the geometric representation of your mills. So first is your ball mill. Okay, it's the simplest form of your mill. Okay, metal balls, ceramic balls or rubber balls, whatever kind of material of construction of ball is, that is used in the mill. B is your planetary mill. So here you can see that the 2 cylindrical vessels are attached, but they rotate on their axis. Okay, so that is your planetary mill, right? The axis rotates and your mill individually, they also rotate together, and inside the mill you have kept the balls. Third one is your vibratory mill. So here you can see that vibration motion is responsible for the breaking down of your material. Okay, in the arrow you can see that your mill, it moves horizontally and vibration is created. D1 is your stirring mill. So attrition is the major force which is responsible for the breaking down of your particles. So you can see in the figure D, I have a cylindrical vessel in which paddle agitator is kept and balls are filled here. So when your material is inserted, the main force which acts on your particles, okay, that is your attrition. E kind is your pin mill. Okay, so here instead of balls, horizontal pins are responsible for the breaking down of your material. And F is your rolling mill. As simple as that, you can see that between 2 rollers, your material is fed, and because of the counter motion of rollers with respect to each other, the material is crushed out. Okay. So first here you can see the attrition mills. Okay, this is the schematic figure of your attrition mill. Here you can see that inside the vessel, balls are filled and a rotating impeller. Okay, the rotating impeller, it moves, and because of that, balls are also able to move along the cylinder. And the material is hence, okay, as the material is reduced in size because of the attrition. Next is your pin mills. So here you can see how pin mills work. Okay, this is the figure of your pin mill. You're feeding the material from the top, okay, and then because of the rotating plane, this whole assembly, it rotates together, and the pins create reduction of the particles. Clear? So see, on the left hand side you have your figure of a vertical pin, and on the right hand side this is a figure of your horizontal pin, right? Now let's see about the attrition example. So here you can see that for different material, my attrition technique also changes. So first is for FeCO powder, that is your iron cobalt powder generation, the general type of technique you use is the rotary ball mill. The grain size which can be obtained here is what, 10 to 15 nanometer, and the time required for attrition is about 30 hours, right? Next is simple for your iron composition. Then you are using what, vibratory mill. The grain size obtained is what, about 20 nanometer, and the attrition time is about 4 hours, right? Similarly, if the composition of now the particle is what, NiAl, okay, for nickel aluminium kind of material, then again you use vibratory. Similarly for nickel silicides, okay, again you use vibratory mill. So here you can see that for different kind of material, my grain size also changes, and the attrition time also varies. Okay. Then for FEC, you use horizontal ball mill. The grain size obtained is about 4.7 nanometer. and the time required is 500 hours. So you can see that you require such a large amount of time. Okay, so here you can relate your cost factor, that in your ball milling the cost increases because the operation time is very large. Now that was about your chapter number 2, that is the synthesis of your nanoparticles. Now we will be starting our chapter number 5, that is the fabrication of your nanoparticles. Okay, so in this chapter the contents are what you will be studying about: lithography, chemical vapor deposition, physical vapor deposition, sol gel synthesis, molecular self-assembly, crystal growth, epitaxy, etching, masking. Okay, so to fabricate new kind of nanostructures, we use this technique. Once nanoparticles has been created, okay, once nanoparticle has been created, then if you need those particles to fabricate into useful nanostructures, then these techniques are used. So let's start with sol gel method. So the two important points about this method is what? First of all and foremost, that it is your bottom-up approach method. Okay, from the tiniest entity we are going towards the nanoparticle size. That is the gist of your bottom-up approach. Then it is your liquid phase synthesis method, right? So now let's see. So in sol gel method, what happens? Forming a solid gel in a liquid phase from a suspension consisting of a solid metal salts. So what you need a suspension of solid metal salts, and from that you are creating a solid gel in a liquid phase. Okay, but what is agent you here used is, we use catalyst. Okay, so sol represent a suspension consisted of liquid and solid particles, while gel, it represents the solid state of this suspension. Once again read it. What is your sol? It represents a suspension which has liquid and solid particles, but gel, it shows you the solid phase of your suspension. Clear? Now, sol gel method, it is primarily used for ceramic production. Okay, so if I need my nano ceramics, then especially for that purpose, sol gel technique is used. Now, this is the important point. The sol gel process is based on hydrolysis and subsequent condensation of metal oxide pre-initiators. So what kind of pre-initiators we are talking about? Such as nitrate, sulfate. Note down, nitrate and sulfates are your pre-initiator. Okay. So this condensation can occur with or without catalyst inside ethanol or water-based acidic or basic solution. Okay, what is condensation? Two small molecules, when they attach together to give you a big molecule, but with the liberation of water molecule, that is your condensation. Okay, in polymer chapter you might have studied about the condensation. Okay, so here you can see that alkoxide present inside a water alcohol solution are removed from the medium through hydrolysis by pre-initiator. So this is the step 1. What you are doing in your water alcohol solution, you are removing the alkoxide using what? Pre-initiators. Okay, this metal oxide bonds are formed from the metal that remain in the structure after hydrolysis, and they create a mesh-like structure. Okay, by growing to make the whole volume consisted of a metal oxide and once again a metal, and then gel is formed. So how the progress initiates, that a mesh-like structure is growing, which consists of a metal oxide and a metal. Okay, this attained gel, it is left for aging, and porous gel or nanomaterial production happens by burning with high temperature processing. Okay, so now the step is what? It is left to age and it grows continuously. Okay, so what are the stage of production? Here you can see that first of all is your hydrolysis of pre-initiators. First step is what? Hydrolysis. Second is your condensation. Okay, third is your gelling. Fourth is, in gelling what happens? Mesh-like structure is created. Then comes your fourth step, aging. You let this mesh-like structure to grow itself. Okay, then fifth is drying, and sixth is your high temperature processing. Clear? So let's see about the reaction. So first is your hydrolysis. So you can see that MOR, that is your metal oxide, alkoxide, okay. They react with water to give you MOH plus ROH, okay. ROH is your ethanol, right. Then is your water condensation. So you can see that MOH and MOH, two metal oxides, they combine together to give you a big molecule with liberation of your water. So that is your water condensation. In the third step, okay, in the third you can see that it is your alcohol condensation, because now alcohol is removed, okay, when two small molecules combine together. So what are the components of your sol gel method? We already saw we need a pre-initiator, you need a solvent, okay, we already discussed a solvent is needed as it is a liquid phase reaction. Third is your catalyst. So you can see that. So first of all soluble pre-initiator can be used in your sol gel process, okay, the pre-initiator should be soluble. These can be defined under two main groups. You have metal salt or alkoxide. So as a pre-initiator, you can use a metal salt and a alkoxide, okay. So for metal salts, what are the metal salts? The general formula is what? MnXn, okay. M is your metal, X is the anionic group, whatever it is present with your metal. For example, AlCl3. Aluminium is what? That is your metal. Cl minus, chloride ion, is your anionic group, okay. Anionic means negative charge. So right, this is about your metal salts. Now about the metal oxides. You can see that metal alkoxide. What are the alkoxide you can use? Okay. For methanol, its alkoxide is what? Methoxide. Okay. For ethanol, your alkoxide is what? Ethoxide. Similarly, for 1-propanol, 2-propanol, you can see it has corresponding alkoxide. So these are the kind of alkoxide which you can use as a pre-initiator. Now, about important note about your metal alkoxide is that these alkoxides, they actively participate in the reaction, okay. These components are highly reactive in presence of humidity, heat or light. So you can see that when your reaction is being carried out, the suitable conditions are what? That you need heat or light or humidity, because if you are using metal alkoxide, it increases its reactivity, right. So this was for today's lecture. In next lecture, we will continue with the sol gel technique. Thank you.